Hi everyone, welcome to our class. Today I am going to discuss the derivatives of trigonometric functions. At the end of this video, you are expected to be able to use the theorem, the limit of sine alpha over alpha as alpha approaches to 0 is equal to 1 in the derivation of the derivative of a trigonometric function. Identify the appropriate formula in finding the derivative of a given function and find the derivative of a given function. Let us now prove the theorem the limit of sine alpha over alpha as alpha approaches to 0 is equal to 1. We will be using this theorem in deriving some formulas for derivative of trigonometric functions. So as proof, we are going to consider a triangle ABC circumscribing a sector CAD. So we have CA in here is a radius. Then we have there the sector CAD with AD also equal to the radius. And inscribed is a triangle DAE. So we have DAE. You will notice from this figure, the common vertex is at A. Let us denote the included angle in vertex A as alpha. Let us let also the area 1 be, or area of the triangle BAC be denoted by A sub 1. The area of the sector CAD be denoted by A sub 2. And the area of the triangle DAE denoted by A sub 3. So from the figure and comparing their areas, we say now that the area of the triangle BAC, which is A sub 1, is greater than the area of the sector CAD, which is A sub 2. And it is also greater than the area of the triangle DAE, which is A sub 3. Also from trigonometry, you remember that the area of the triangle is equal to 1/2 times the product of the perpendicular sides. So from the figure, we have A sub 1 will now be equal to 1/2 times BC times AC. So also from the triangle ABC, we have tangent alpha. So the angle alpha, it's the opposite side, BC, over the adjacent side, which is AC, or that is equal to R. So BC then is equal to R tangent alpha. We also know that tangent alpha may be written as sine alpha over cosine alpha. So substituting now the values, we have 1/2 times BC, which is R sine alpha over cosine alpha, times AC. Looking at the figure, AC is equal to R. So that gives us now A sub 1 is equal to R squared sine alpha all over 2 cosine alpha. Also, the formula for a sector of a circle is equal to 1/2 the square of the radius times the central angle alpha. Then we have there the smaller triangle DAE. Again, we have the formula A sub 3 is equal to 1/2 times the product of the perpendicular sides. Again, looking at the figure, we have now 1/2 DE is the side. So looking at this triangle, we have sine alpha. Sine alpha is the opposite side, which is DE, all over the hypotenuse with this, which is R. So solving now for DE, that gives us R sine alpha. So substituting now the values, that's R sine alpha. And we have AE cosine alpha is equal to AE over R. And you have in there AE, solving for AE, we have R cosine alpha. That gives us now A sub 3 is equal to 1/2 R squared times sine alpha times cosine alpha. Going back to the inequality, A sub 1 is greater than A sub 2, which is greater than A sub 3. Substituting now the values, that will give us R squared sine alpha over 2 cosine alpha. It's greater than 1/2 R squared times alpha, which is greater than 1/2 R squared sine alpha times cosine alpha. So if we divide each member by 1/2 R squared sine alpha, this will now becomes 1 over cosine alpha greater than alpha over sine alpha, which is also greater than cosine alpha. So taking the reciprocal of the inequality, we now have cosine alpha is less than sine alpha over alpha, which is less than 1 over cosine alpha. And as we let alpha approaches to 0, you will notice in here that cosine alpha will also approach to 1. That means the limit of cosine alpha as alpha approaches to 0 is equal to 1. Similarly, as alpha approaches to 0, here 1 over cosine alpha will approach to 1. Therefore, the limit of 1 over cosine alpha as alpha approaches to 0 is equal to 1. So take note in here that cosine alpha is, or the limit of cosine alpha as alpha approaches to 0 is the left-hand limit of the function sine alpha over alpha. Similarly, the limit of 1 over cosine alpha as alpha approaches to 0 is the right-hand limit of sine alpha over alpha. The left-hand limit and the right-hand limit being equal, it follows then that the limit of sine alpha over alpha as alpha approaches to 0 is equal to 1. Let us now find the derivative of y is equal to sine x using the delta method. So to solve, we start with substituting x by x plus delta x and y by y plus delta y. So that this function now becomes y plus delta y is equal to sine of x plus delta x. The next step is to solve for delta y. So we just transpose y to the right. That gives us now delta y is equal to sine x plus delta x minus y, whose value is sine x. Then in trigonometry, we have our sine sum, which is equal to sin cos cosine, or we have sine a plus b is equal to sine a cosine b plus cosine a sine b. So we can apply now this formula for sine x plus delta x. That will give us now delta y is equal to sine x cosine delta x plus cosine x and sine delta x. Then minus sine x. We could rewrite this function writing first cosine x sine delta x. And in these two terms, notice that sine x is common. So we can factor out minus sine x. That gives us 1 minus cosine delta x. And in trigonometry, again, you have the half angle formula where sine squared a is equal to 1 half 1 minus cosine 2a. So notice that this expression 1 minus cosine delta x looks like the 1 minus cosine 2a. Now when applying this formula, 1 half and 1 in here are constants, while the angle of sine at the left side is 1 half the angle of cosine. Okay, so we now have the delta y equal to cosine x sine delta x minus sine x. The 1 minus cosine delta x can now be solved using the formula, and that would give us 2 sine squared. The angle of sine at the left side is 1 half the angle of delta x at the right side. So we have 1 half delta x. We continue our solution by dividing this equation by delta x. That gives us now this equation. Then the next step is to evaluate the limit of the function as delta x approaches to 0. That means we're going to evaluate the limit of the left member as delta x approaches to 0, and we find also the limit of the right member as delta x approaches to 0. And applying some theorems on limits, that will give us now the limit of delta y over delta x approaches 0 is equal to, we just find the limit of each term. So we have the limit of cosine x sine delta x over delta x as delta x approaches to 0 minus the limit of sine x times 2 sine squared 1 half x, 1 half delta x over delta x as delta x approaches to 0. Applying again some theorems on limits, where when we evaluate the limit of, we have here products, we can evaluate the limit of the factors. So this symbol, the limit of delta y over delta x approaches to 0, may be written as dy over dx. So limit of these factors may be written as the limit of cosine x delta x approaches to 0 times the limit of sine delta x over delta x as delta x approaches to 0. So take note how we separate the factors. We are anticipating in the second factor for us to be able to apply the theorem the limit of sine alpha over alpha as alpha approaches to 0 is equal to 1. Similarly, in the second term, we can separate in here the factors. Take note that the angle of sine in here is 1 half delta x. So we must also have a factor in the denominator equal to 1 half delta x. So we can just write these two as the denominator of this denominator delta x. So we can now separate the factors as the limit of sine x times sine 1 half delta x. So there are two sine 1 half delta x. So we separate one together with sine x, and the remaining factor in here will be the sine 1 half delta x over 1 half delta x, for us to be able to again apply in here this theorem. So simplifying, evaluating now the limit, we substitute or we apply this theorem, whichever is applicable. So for the limit of cosine x, since there is no delta x in here, we just copy cosine x. Then the limit of sine delta x over delta x, we can apply this theorem that will be equal to 1. Then we have in here the limit of, we have sine x, so we just copy sine x. And then we have sine 1 half delta x, so we substitute delta x equal to 0. So sine 0 is 0. And then the limit of sine 1 half delta x over 1 half delta x, applying this theorem, is equal to 1. Simplifying further, we now have this is equal to cosine x. This is 0. Sine x times 0 times 1 is 0. So, knowing the value of y equal to sine x, that gives us now then the derivative of y, whose value sine x is equal to cosine x. Or, generally, if u is a function of x, where u represent the angle of sine, then we now have the derivative of sine u, therefore, is equal to cosine u times the derivative of u. We now have in here the derivatives of the trigonometric functions. So in the following formula, u, which represents the angle of the function, is a function of x. So we have here the derivative of sine angle is equal to the cosine angle times derivative of the angle. Derivative of tangent angle is equal to the square of secant angle times derivative of the angle. The derivative of secant angle is equal to secant angle tangent angle times derivative of the angle, while the derivative of cosine angle is equal to the negative sine angle derivative of the angle. The derivative of cotangent angle is equal to the negative square of cosecant angle derivative of the angle, and the derivative of cosecant angle is equal to negative cosecant angle cotangent angle derivative of the angle. So I hope you will find time to explore or derive some of the trigonometric function formulas or derivatives of the trigonometric function formulas found in the list. And maybe there are some guides that you can apply in memorizing the formulas. The pair functions are sine and cosine. We have here cosine and sine. The other pair functions are tangent and secant. And the pair functions cotangent and cosecant. Also remember that the derivative of the C functions, derivative of cosine angle, derivative of cotangent angle, derivative of cosecant angle are negative. So the other techniques that maybe you can apply in memorizing the formulas will be for you to explore. Let us now apply the formulas for the derivatives of the trigonometric functions together with the basic differentiation formulas as we solve for the derivatives of the given functions. We have here y is equal to sine 4x, and we are required to find for the derivative of y with respect to x. So we start our solution by finding the derivative of the left number with respect to x. We do the same, find the derivative of the right number with respect to x. So this is now our dy over dx. While at the right side, we have derivative of sine angle. So if you're familiar with the formula, we know that the derivative of sine angle is equal to, in the next step, recite the right side of the formula. We have that is equal to cosine angle times the derivative of the angle. So further, we have now derivative of y with respect to x equal to cosine 4x, and the derivative of 4x, we have product 4 times x. So since 4 is constant, we write that one outside, and the derivative of x with respect to x is equal to 1. So finally, we have derivative of y with respect to x is equal to 4 cosine 4x. Then we have z is equal to secant t over 3, and we are required to find for the derivative of z with respect to t. So take note in this symbol. This denotes that z is our dependent variable and that t is independent variable. So as we perform the differentiation process, when we say derivative, we will be taking derivative with respect to t. So we have here the derivative of z is equal to the derivative of the secant t over 3. And as we write the symbol the derivative, take note we have our d over dt. So we have now dz over dt, or the derivative of z with respect to t, is equal to, then we have derivative of secant angle is equal to secant angle times tangent angle times the derivative of the angle. So here we just copy and notice that for the derivative of t over 3, we could have used the derivative of quotient. But since 3 is constant, we can just factor out instead 1/3 times t. So we can apply here the derivative of product. With 1/3 a constant and the derivative of t with respect to t equal to 1, that gives us now secant t over 3 tangent t over 3 times 1/3. So we have our final answer. The derivative of z with respect to t is equal to 1/3 secant t over 3 tangent t over 3. For the function y is equal to cosine the quantity 3 minus bz squared, we are required to find for the derivative of y with respect to z. So this symbol tells us that y is the dependent variable, z is the independent variable, and therefore b in the given function will be treated as constant. It is also important to note in here that the exponent 2 has its base 3 minus bz. That means this whole function, the square of 3 minus bz, represents the angle of cosine. So as we find for the derivative of y with respect to z, we also find for the derivative of cosine and its angle, the quantity 3 minus bz raised to 2. We have now derivative of cosine angle. So applying the formula, derivative of cosine angle, that is equal to negative sine angle times the derivative of the angle. So further, we just copy derivative of y with respect to z because that is what is asked. This does not contain derivative, so therefore we just copy. Then we have here derivative of 3, the quantity 3 minus bz raised to 2. So looking back again to the list of the differentiation formulas that we had, we have the derivative of power. The derivative power states that the derivative of base raised to an exponent is equal to, we write that one in the next step, the exponent times the base raised to the exponent minus 1. So we have 2 minus 1, that's 1, times the derivative of the base. Again, we copy those factors which do not contain derivative. Then we have here derivative of 3 minus bz. So the function following the derivative contains two terms. So we find for the derivative of each term. The derivative of 3 minus the derivative of bz. So further, we can arrange in here the factors. A negative sign, 3 minus bz raised to 2 times 2 times 3 minus bz may be written as negative 2 times 3 minus bz times sine the quantity 3 minus 2z raised to 2. Then we have the derivative of 3, which is a constant. 3 is a constant, so the derivative of 3 is 0. For the derivative of b times z, since b is constant, so we can just factor that out. That will be minus, so derivative of 3 is 0, minus derivative of bz is b, derivative of z with respect to z is equal to 1. So we are now done differentiating. Take note, this is a factor. 0 minus b is negative b. We can combine that one with this constant factor negative 2, giving us now 2b times 3 minus bz times sine 3 minus 2z raised to 2. For the given function, w is equal to cosecant cube pi over 4 minus x over 2, we are required to find for the derivative of w with respect to x. So in this given trigonometric function, it is important to note that the exponent 3 actually has its base cosecant and its angle pi over 4 minus x over 2. And so therefore, in differentiating the function with respect to x, we write this function as the quantity cosecant pi over 4 minus x over 2 raised to 3. So the base of the exponent 3 is the whole function cosecant angle. So in finding for the derivative, looking at the given function following the symbol, we have now in here the derivative of a function in power form with this as its base and the exponent. So the power formula states that the derivative of power is equal to the exponent, this is the exponent, times the base, this is the whole base, cosecant pi over 4 minus x over 2, raised to the exponent minus 1 times the derivative of the base. So the derivative of cosecant pi over 4 minus x over 2. Okay, so we just copy this factor. Then the derivative of cosecant angle. Again, we have the formula for the derivative of cosecant angle. That is equal to the negative cosecant angle times cotangent angle times the derivative of the angle. So we look at this function, notice that these factors in here do not contain derivative. We only have this one. So we can now combine similar factors or factors having the same basis. So we have this and we can collect these two factors that will give us now in 3 and negative 1, we have negative 3 and we have cosecant pi over 4 minus x over 2, quantity raised to 3, this 2, and we have one factor in here. Then cotangent pi over 4 minus x over 2, derivative of pi over 4 minus x over 2. So there are two terms. With pi over 4 a constant, its derivative is 0. And x over 2 again may be written as 1 half x. So its derivative is we just have minus 1 half. So we're done differentiating. We just collect the constant factors and we now have our final answer. So negative 3 and negative 1 half is positive 3 halves. This factor may be written with the exponent 3 between the cosecant and its angle. So we have derivative of w with respect to x is equal to 3 halves times the cube of cosecant pi over 4 minus x over 2 times cotangent pi over 4 minus x over 2. That will be the final answer. There are still many differentiation formulas that you will encounter for the different transcendental functions, and you are advised to memorize them all. The best way to memorize the formulas is to apply the differentiation process as much as you can and recite each as you apply it. So I will end up my discussion in here. Thank you for watching. I hope you learned something.